Hello, everybody. This is Sunday. This is January 30th, and we are moving into week 4 of our online astronomy class. This is the second module. We had module 3 last week that was about the laws of motion and Newton's laws of gravity. This week is our second week of the laws of nature, the laws of physics that allow us to understand how the universe works. And module 4 is about light. It's about both what the nature of light is, and it's about how we gather light using telescopes. And speaking of telescopes, great news on the James Webb Space Telescope. A couple days ago, it arrived at its final location. It did a final burning of its thrusters to go into orbit around an empty spot in space. It's just where the gravitational forces of Earth and the moon and our own rotation around the sun, all of that combined, give you a sort of a stable spot in space where the James Webb Space Telescope can stay and make its observations. So the Webb Space Telescope is there. It has completely unfolded. All of its mirrors, it has 18 mirrors, hexagonal mirrors, and each one of those has 6 little motors behind the mirror that can change the position of that mirror and even change how much the mirror is curved. And those are all working. So everything is working. The telescope is now going to cool down for 6 months and then send back its first pictures. So very, very cool. And like any telescope, what the James Webb Space Telescope does is that it gathers light. All astronomers can do is look at stars. That's all they can do. And they can look at stars, they can look at planets, of course, and other things. But when they look at those stars and the planets, what do they see? They see light. And so all the information that comes to us from stars and planets and galaxies is carried by light. Now, if we see those lights, if we see those stars or planets moving from night to night, we can use Newton's laws of motion and gravity to understand something about those stars and planets. We can figure out what their masses are, for instance. But what can we figure out just from the light itself? That's what we're going to be finding out about. And the first thing to know about light is, what is it? Okay. Light is just waves of magnetic and electric energy. You've heard of magnetic fields. You can pick up a paper clip with a magnet. And you've also perhaps felt electric fields whenever you have static electricity. If you've ever rubbed a balloon on a piece of cloth and you move it over your hand, you can feel the hairs of your hand stick up. Same thing if there's static electricity on clothes coming out of the dryer. That may cause the hairs on your body to move slightly. And those hairs are responding to the electric field surrounding that object that has an electric charge. Well, light is made of electric and magnetic fields, electric and magnetic energy. And as that energy is coming towards you, the energy isn't coming just nice and smoothly, it's actually pulsing. And so as those pulses move across, I can also illustrate that like this: as the pulses move across, you have a wave of pulses of magnetic and electric energy. And those pulses go very fast. They go like 100 million times a second. So you don't see things, grow bright and dim and bright and dim and bright and dim, because, 100 million cycles of that per second that light has, visible light has, is much too fast for our eye to even notice. So that's what light is. Also, I mentioned that light has a waveform, and I can use a waveform. Of course, the light wave isn't itself moving up and down. What's happening is that if I say the wave is high, that means that there's a lot of energy there. And if the wave is sort of in the middle, that means there's not much energy there. So that's what all the wave represents, those pulses of energy. But also, what carries the energy actually in the light wave is little particles of light. These particles of light have no mass. They're just little packets of energy, and they're called photons. And so you'll be learning about how photons carry so much energy with, carry so much information with them. They carry energy and they carry information. And it's just an amazing thing that astronomers can use telescopes that can actually count photons one by one as they come in from a star. So, where does light come from? What gives off light? And the most important sort of light there is in astronomy is called blackbody radiation. And blackbody radiation is the heat radiation, not the heat radiation, I shouldn't say it that way, is the light, the radiation, and those two mean the same thing. Light and radiation mean the same things to an astronomer. So blackbody radiation is light that is given off by any object that has a temperature above absolute zero. Now, absolute zero is as cold as you can get, so everything has a temperature above absolute zero, and that means everything gives off blackbody radiation. In fact, you're giving off blackbody radiation right now. You are, and you can detect it, not with your eyes, because our eyes can only detect a small part of the total range of wavelengths. That's called the spectrum of light. Our eyes can only detect a small part of that total range or spectrum of light. So we are right now shining. And in fact, you're shining at about 100 watts right now in infrared light. And you can feel that. You know, if you want to, you can close your eyes right now. Oh, go ahead, close your eyes and bring your palm up in front of your head. And bring your palm with your eyes closed. Bring your palm so it's almost touching your forehead. And just before you reach your forehead, you'll feel some heat. And that is the blackbody radiation, the infrared blackbody radiation that your body is giving off. Now, if you heat up an object even more than that, it gives off visible light. And that's why the stars are giving off light. It's because their surfaces are so hot. Like our sun gives off light in a continuous spectrum of wavelengths. And a continuous spectrum of wavelengths just means that all the colors of the rainbow are there. And you can see over my shoulder here, there's a rainbow. And all those colors that you see are present in the white sunlight. And white is just a combination of all of the colors. So that blackbody radiation is what astronomers study. And it can tell them from the colors of the stars, the blackbody radiation from stars tells us the temperature of the stars. If you have an electric stove, or you've seen an electric stove, if you turn it up a little bit, it glows a very dull red. And then as you turn it up hotter, it glows brighter and sort of towards the orange. And if you had a super stove, you could keep turning that up. And pretty soon you'd be seeing other colors of light being given off, green and blue and all the colors that are in blackbody radiation. Now, I've made a couple videos, and one of them is about blackbody radiation, and I turn up the filament of a light bulb to make it hotter and hotter, and you can watch as the sort of colors given off by that filament change. So that is one sort of light that there is, and it's the main tool. Blackbody radiation is really one of the main tools that astronomers use to study stars. So what else can I tell you? I can tell you that how do we know what stars are made of? How can we tell what stars are made of? You know, you would think it was impossible. In fact, in the early 1800s, some philosopher says the one thing we will never know is the composition of the stars, what elements make up the stars. And already at that time, they were doing experiments that would prove him wrong. And it turns out that this all has to do with how atoms absorb and emit light. It turns out that for stars like the sun and a lot of other objects too, if you have cool atoms in the star's outer atmosphere, they can absorb just certain wavelengths of light from the continuous blackbody radiation that's coming from the hotter sun below. And that means that at certain wavelengths, the spectrum, the spectrum of colors, just like this spectrum behind me, this is the continuous spectrum of sunlight. But if you really looked at it closely, you would see little black ridges in it, going up and down that spectrum. And those black ridges are where some of the light has been absorbed by atoms in the star's atmosphere. And what light is absorbed depends upon the elements that make up the star's atmosphere. So we look at the light, we look for those dark lines where light has been absorbed, and the pattern tells us what stars are made of. It's like a fingerprint. Every element has its own fingerprint. And by looking at the spectra of starlight, we can figure out from those fingerprints what elements are in the stars. So we do know what stars are made of. It's an amazing, amazing thing. Now, what else can light tell us? Well, if you've ever heard a train coming toward you and it's blowing its whistle as it goes past you, you notice that the pitch of that changes. Or maybe the same thing if you've ever seen an ambulance going by you. Because as the ambulance or the train is approaching, the pitch is higher. And as it's moving away, it's lower. So it sort of sounds like this. So here is the horn moving along, and as it's coming towards you, it sounds higher. And as it passes you, the pitch drops lower. Let me do that again. I've been practicing this, so I'm going to do it again. Here we go. And so just as that source of sound is passing you, it changes from a higher pitch when it's approaching to a lower pitch when it's moving away from you. Same thing for light. When a source of light is moving towards you, it's catching up with its own light waves. And those light waves are compressed. And so the light looks a little bit bluer. And as the light source is moving away from you, it's moving away from its own light waves. And so that stretches out the waves. And the light looks a little bit redder. Now, it's really the color of the stars that determines their color. You know, stars aren't moving fast enough for this Doppler effect. That's what we call the shifting of the color of light, for the Doppler effect to have a big effect. But we'll see later that it does have a big effect when it comes to looking at things that are far away from us, like galaxies. Also, you can look at I mentioned the dark lines that are in the star's spectrum. And that means that those dark lines, if here are dark lines, for instance, in the spectrum of the rainbow that's behind me, those dark lines might shift back and forth. And that would tell me how that object is moving. And that can help us figure out how things move. So all sorts of tools in the astronomer's toolkit. Finally, I'll just briefly mention telescopes. Telescopes are big light buckets, right? Big light buckets that capture starlight. The bigger the telescope, whether it's a lens or a mirror that the telescope used to focus the light, the more light can be gathered with a larger lens or mirror. And that means that you can see fainter and fainter objects. Also, if you have a bigger mirror or a bigger opening for your telescope, whether it is a lens or a mirror, then you can see more detail in what you're looking at. And that's called resolution. So the bigger the lens or mirror, the more resolution the telescope has. So I hope you enjoy learning about light. We'll be referring to these this module, the contents of this module, a lot as we go through the course in order to understand how we learn these things that we learn. Finally, let's take a quick look at Stellarium. I'll pull up Stellarium here and show you what's going on in the sky. Now, usually when I pull up Stellarium, we're looking south, but right now we're looking north. And I've set the sky up. This is February 1st. This is Tuesday. That is the day of the new moon, and so there's no moon in the sky at all. And usually we're facing south, but right now we're facing north. And facing north, if you look over here slightly to the northeast, you can see the Big Dipper. The Big Dipper is sort of standing on its handle. Here is the bowl of the Big Dipper. Here's the handle of the Big Dipper. And right now, at 9 in the evening, it's standing on its handle. I'll just point out two of the stars that are in the Big Dipper. This star right here is called Merak. And you know, if you click on a star in Stellarium, here's information that comes up about it. You can get rid of that by right-clicking. So here's Merak. This star is named Dubhe. And Dubhe is the state star of Utah. No kidding. And if you draw a line from Merak to Dubhe, these two stars at the end of the bowl of the Big Dipper, and follow them across the sky, you run into the North Star, Polaris. So that's how to find the North Star in the sky. The North Star is not all that bright, but it hovers right over Earth's North Pole. So here's Earth's North Pole. And that means that as time passes, the other stars appear to revolve around Earth's North Pole. So if I go from night at night to 10, 11, 12, all the other stars appear to move around the North Pole due to Earth's rotation. So I'll just move back now to night at night. So go out, take a look at the Big Dipper tonight and see if you can find the North Star. Well, there's a lot in this module 4. I hope you enjoy it, and I hope you have a great rest of your week, and I will look forward to seeing you next week. So take care, and I will see you soon. So till then, bye-bye.